Welcome back to the fourth video in my series about StackIt. Last time we had a bit longer episode where towards the end I confused myself quite a lot. We implemented the first draft of our MinMax algorithm and today we're going to continue. A couple of things I want to do is maybe we're going to test it a little bit more and see if we need to debug it or figure it out. Whether we have some issues with it, and after that I want to start implementing the performance function. This is just because I think it would be really interesting to print some statistics, and after that we could see if we improve the interface first and play our own AI or let it play itself. And what else can we do? Next, I would actually say we start improving it a little bit, because currently it is just a greedy search. It won't search very deep, maybe even already deep enough to not be beaten by me, but I think there's a lot of room for improvement. So one thing I've been doing in the meantime too is I've started adding some tutorials, which is basically following the videos more or less. The first two videos I kind of have in one file because it was kind of basic things that we did, and last time after I ended the video I actually played with it a bit more, tried to figure out why I got so confused, and so just to make sure that I didn't add anything that wasn't shown here on the video, I will just show you the diff that I'm going to commit. So we imported deep copy in our GamePy. This is for our undo, and you can see we added a history. This is for undo. We added the other player function. We added the possible moves. We added the boxes for. This is all for our MinMax algorithm. Here's the undo. I think this one might not have been in the last episode. I actually improved the output where we now print the number of moves that have been played on the current board and which player is currently, which player's turn it is. Here maybe even that has not been there, so I changed the board that I'm testing on a little bit to have some more interesting cases, and I changed the run game function. Maybe I even renamed it. This is our game loop. Now we can pass a board and just start playing there. So I was going in between playing on the board and running the AI and trying to see if it makes reasonable best move scenarios, and just in order to figure out if there's anything buggy. So we will commit this, and we will also add our MinMax, and we will add the tutorials 0 to MinMax. Writing the tutorials I'm not quite finished. I will still add it already. Yep. And the rest is just could be in the git ignore. Also, this is we don't need this, and then we do, what did we have? .pytest and cache, correct? PyTest cache, okay, it didn't take a look at PyTest. Yeah. Okay. So just push this, and then we start. And then let's actually make a split here, so we can work in both files. Okay, what did I say we do? Yeah, first let's just see where we are. Let's just execute this. This is currently in the run board move, so maybe even this has not been shown in the last episode. I kind of added in one ISAP prompt, so now if we are player one is green. Maybe I should color this output as well. Yeah, so if we place on here, it falls over, and then we go to 1 and 2, and then it falls over as well. So, and yeah, I added an exit as well. Yeah, this is just me, and if we now ask the AI what's the best move, it will calculate for a while. It now searches to the depth of 6, which means it plays 6 moves, and here it tells me if player 1 plays at 0-0, the expected outcome is 2. I'm not sure we had this the last time, but our function returns the best move and the best score. One thing I think I found last time is I had to switch up the boxes for and other player. Let me just change this up slightly. This one will now be our execution, and here we split it with the MinMax, and we just work in a single vim up here. I liked it a little bit better. So for now, I think we just go with the performance function, the famous, miraculous performance function, or performance test. So I will make it so that we can pass it aboard. It will make an AI, and we actually will slightly change the. Oh, why not? So what performance should do now is we will start from depth 1 and then search the best move, start from depth 2, depth 3, depth 4, and so on. And on the way, we want to print some statistics output. So for let's just go 5 for now. So we create one of those AIs. These AIs get this move. Score. So maybe actually this should live in the algorithm itself. I thought it would be nice if later on we could pass different algorithms to see how it changes. But if we put it in our algorithm, it might be nicer to print the statistics, because now we need to calculate some statistics around this best move, and I kind of don't want to pass this to the outside world. Let's just see. For now, we're just gonna print. We're gonna make the output a bit sparse, like this. Here we want the max depth, and here we want the best move, and here we want the score. So this could be a most simple Perft function. It doesn't show us a lot. I have one more thing, and we want, of course, t0 equals time, and then here we print C0. Import it like this, and then let's see if we take our fancy board, Perft board. Does this work? Does not. Get best move. Best move depends on the board, of course. That was fast. So, okay. One second. Can't barely see anything. Maybe we should make it a bit nicer. Like this, starting performances, and then we could and a bracket, and then we shouldn't do so many other things. This one is a bit annoying. Oh, whoa, sorry. Does that not work? Oh god. Why does this not work? Now I have to comment it like this? Oh no. Oh, sorry for that. Okay, we are here. So we can see at depth 0, it immediately returns. It basically says, okay, I didn't find the best move because I just score the board, and the score is 0. Is this something we can maybe also print the board before we start? Starting Perft. Print. So, no. So on this board, if we count, there's 2 4s, 2 4s, and 2 3s, so it's a 0. 0 is the best score. If we search to depth 1, which means we make one move and then stop, we can find that if red plays on 1 0 and throws over this 4, red will take away these 3 from green will take away these 3 from red, and yeah, then the overall score will be +6 because 1 falls off the side. Of course, one thing the AI can't see at this particular depth is if red in the next turn throws over one of the 4s, then it will gain a huge advantage back. And that's why you can see if we search just one move further, suddenly it says, oh no, I just play at 0-0 because this is a move where it remains even. Funnily enough, if we go to depth 3, where we would get one advantage again, 0-0 is still the way it should start. So one statistic that we should probably print here, which would be nice, is the principal variation. This is which is the best line that it found up to this depth. And at depth 4, it says, oh, we play at 1-0 again. So this is actually interesting. So at depth 4, it means that it ended on an enemy turn. This is kind of important. What you do in chess usually is if you end in a position and it is possible to take an enemy figure, you will always play all the possible takes, even though you already reached max depth. This is called quiescent search or something, and you do it to avoid this horizon effect where you search until a certain position and you think you're really good, but actually just one move further you're really bad. Interesting enough, this was actually quite fast to search that deep. Okay, it's a very small field. Let's just up this a little bit and see how exponential the exponential tree kicks in. So you can see it's from 0 point something to 5 seconds, and the next one might not even really finish easily. So okay, we said one thing that might be interesting to print is, let me just round this one to 3 or 4. The principal variation, and then also how many moves we evaluated. Yeah, 5 seconds, 35 seconds. But apparently it looks really good for the green player, given that we don't have any more bugs. Okay, we have to go here. So in order to get, let's start with the easy stuff. Stats equals dictionary. Let's make it from import the default dictionary, because I will now just count a lot of things. For example, every time we make a move. So stats moves may increase this one. And now this is the thing why I thought maybe performances should live inside the algorithm. I'm not sure if I will unify the stats that I returned or not, but for now, ugly as it is, I will just do stats. Let's look this here. And then let's reset it. Okay, oops. Yeah, deleted this for some reason. So now you can see this is a little bit easier to look at, and you can see here we search 9 moves, 70 moves, 600 moves, 4,000 moves, 165,000 moves. But you can also see, compared to the previous run, where is it? That maybe it's already getting slower, like 6 seconds, 5 seconds, oh no, maybe not. It's hard to say, so we can definitely see if we get faster or slower and how deep we can search in a given time. And I expect and hope that with some of the improvements that we're going to make, that we can search a lot deeper. 1 million moves for 7. And the next thing to print would actually be the next thing to print would be the principal variation, and I thought about this a little bit already. So what we want to store is in each depth what's the possible best move. And for this we want to store principal. This is gonna be a empty list with the size of depth. And I actually want to rename this. Oops, what did I do? I think I can rename this area. No, I shouldn't. That's the next step. Yeah, it's the current depth. Yeah. Okay. This is fine. Principal variation. So now we have an array that is the size of our maximum planned search. Of course, if we were to run in a tournament setting, we need to change this so that it kind of is unbounded, because depending on how much time we have, we might just search deeper and deeper, right? So, but for now, I will limit it by depth. Later on, we can maybe adjust it. And now in every depth, we will eventually go into this best move. And here, so here we want to store the best move of the current depth. Let me think about it a little bit. I think if we just now do something like principal variation, so if we just do this, then we might override the best variation with moves that are not optimal, because we search one branch of the tree, and we find this is the best branch, and then afterwards we search another branch of the tree, which locally might have a better move, but it will never be taken because one of the parent nodes is already worse, overall worse. You can see 5 million nodes down here. And it took us 200 seconds. The principal variation stores the move. From now we can check how it looks, but I think this will just be wrong. Principal, this is print the whole array. And so index, yeah, it's 0 indexed. And now we need to read it from right to left. So the first move will be right. This is maybe confusing, so let's do let's do it like this, and it should work. Yeah, so here you can already see this not working. It's not possible that you put a stone on the same spot twice. So let me think a little bit. We do you find the best move. Ah, I think it should be like this. So, and then we need a local principal variation. And here local principal. What if we just pass through a list? Oh, maybe this is even easier. Let's just make this a list and we pass it in. Principal variation, and we in every principal variation we pass it in, and in every, does this work? Let me think. Recursive algorithms always fuck my mind a little bit. This one still needs to be non times max depth. Let me just run this. 3, 2, 2, 2. That seems wrong because it needs to contain the best move. So it just contains any last searched move, basically. Of course, here this shouldn't be the last search move, but the best move. So again, we have the 0, 0. And this is easier to debug in non-perf mode. So here we go to the AI. And we remove this one and we search to depth. To depth. This guy is not here. 2. No. To depth 2. Let's see if this works. Okay, it says 0, 0, and then one other thing that we wanted to print is also right. So 0, 0, and now what we're gonna do is we're gonna add some debug output. First we're gonna print depth. Current depth. Then we're going to print move, and actually score. Let's just see if this is readable. So you can see a lot of stuff is tried. Yeah. Here we are. Here we are. Yeah. So from here it starts. Oh, no. Damn it. Oof. Let's just fake some input and then it waits for us. So this is the first move that it tries. Here we can see the initial board. And then the first move is top left corner, and then right of that the red player plays. And then the red player tries to play underneath, and the red player plays on its own. Here you can see it throws over the stone, and the next one other thing that we want to print, and I think after this we will also end the episode because it's nearing. Again, is if we found the best score, we want to print this new best. Okay, so we found a new best. Maybe I should make this a bit easier to see. Hashtag Promance programming. Okay, we have a new best. First move, because we don't have anything yet, right? So we say, oh yeah, wait, sorry. I think here it would also be helpful to print the principal variation. Yeah. I think my other approach of the principal variation was more right. I toyed with it a little bit. Okay, best move says nothing currently, which is okay. And then we keep searching. The scores are 0, it's not good. Scores are 2. It's not good. A new best score would be 0, 0, and then 2, 0 is the response to that. 2, 0 is 0, 1, 2 here, just right next to it. So it basically didn't find anything. And we can see that the score puts to it as 0 as well. So can we do better? He puts here, and then red tries and actually puts here. So -3. One thing we saw up here, so it says, oh, we have a new best score. In this variation, if I play on my own stone and red just plays next to my stone, then it's really good for me. Stop it, MinMax. Here. This part. So green played here and red just played here, and then the final score is 5 for green. So this would actually be really good for green. So this is the best move, but then we try, okay, red plays here, okay, it's not better. Red plays here, it's not better. But now red throws over his own stack. And we can see suddenly it got -3 for red. So this would be the best move for red, and actually the first move for green was already not so good. So now you will see that there's a new best move, which once we return, okay, this one also finds 5. Okay, now one level up, we should have found that this is not. Yeah, what's happening? Okay, sorry. This is not so good. Now in this variation we find something. Okay. Let's see. Now we try this. Now we try that. Now we try this. Now we try that. You can see it just tries all the variations and then it finds 0, 0, 0, 0. Why is that? If I remove the board print really quick, I think this might be. It's a bit easier to read in the sense that, okay, we make the first move for green, and now we try all different red moves. And what we can find here is that the worst move that red can make makes red have 0 points, or makes the game even. And the best move that red could make is to make the game the worst move that red can make is make 2 points, which is not good for Now I'm confusing myself again a little bit. I need to think about it, and we will just continue right here in the next episode. I just want to split it at around 30 minutes, otherwise the episodes get way too long. So I will be right back.